Boris is the technical officer of CENSUS, which is the board of the It's hosted by the local department of Meudon. And officer managed and hosted a number of nanosatellites. And today it's going to talk about the this project. And yeah,
thank you, Gabriel. You for the invitation. So you probably know the name of the Observatoire de Paris. This is the castle of Meudon. It's only 50-year-old. Normal facility is in Paris with 350 years old. So we are the young ones. And involved in many space missions in the beginning of space era. So it's not new stuff for us. We have been involved in the James Webb Space Telescope as one of the 4 instruments, MIRI, in the whole European community. Okay, we start in the optical design of MIRI. Great instruments and budgets. We design and deliver ADCS for solar orbiter, which is a full radio astronomy instrument. Flying and tested the ChemCam and SuperCam for the American rovers on Mars. More recently, we have some PI ships on board JUICE, and even more recently, we delivered an instrument, NIRS, that should fly. So that's not a new story, but what is new is this little CubeSat, which was designed by a team of 5 or 6 or 7 maybe crazy fellows, and who delivered the 3 units in 2017. That was launched in January 2018. And so it was tested completely. We've got also traditional facilities of the space lab, so we vacuum chamber. So I know you are very familiar with all of this. What was new is what this and actually on so far. So 10 years later, how are we? We decided that CENSUS we have a special focus on that. The CENSUS is created years ago. Scientists who have an idea with a scientific nanosatellite, and I'm insisting on the fact that we don't make it. That were launched along with InSight to Mars, and that's a picture taken when one of the 2, I don't know which one, was approaching Mars, and here we can see the reflection of Mars on the high-gain antenna. So this is a 6-unit CubeSat, so one of the Marco, and we have many other projects. So this is of course not one of our projects, the JPS project, and inspired by that, we have many projects in the brain. And before going in the technical part of this colloquium, I would like to present the main project we support at the moment. So CosmoCal, for instance, is a good counter example, I would say. So this is to a cosmology project, but the CubeSat is not the observer. The CubeSat is the target. CubeSat is intended to make and to be in space, because if you observe on the top of the mountain, you are in closed fields. It's too close to the antenna. We are talking about very large dishes, like 60-meter diameter, so millimetric observation. And this is way too close. So first we thought, okay, let's make a target which is in a low Earth orbit. But unfortunately, with this kind of you cannot track the low Earth orbit because it goes too fast. So then we ended up with the idea to put a functional payload on the stationary satellite. So it will be time for that. So it should have been a interaction. Eventually, we didn't. If it's not worth doing it. So we suggested that it goes to a geostationary satellite. Then another project is interplanetary project this time is to observe some tracers in the winds of Venus as an additional science case for Envision and the fly around Venus that we go to Venus at the end of the decade. So we target Envision, but it could be another launch opportunity. So this project is supported by Rafael Moreno at Paris Observatory. And this is a millimetric technology that is flying to Jupiter. So we have good results in the Jupiter science case, which is a very cold case. And we would like to reuse it in a very warm situation, the Venus environment. And that's the main challenge, is to make it even smaller, although it is small. Okay, you put your scientific observable here, then you multiply with a reference oscillation that was already multiplied there. And then making a heterodyne mix, you can decrease the spectrum down to 2 gigahertz or something like that, and yet then you can digitalize and have a spectrum. Otherwise, you could not digitalize some quick signal like this. Okay, so this is one of the projects, interplanetary projects. We've got here, and I know that people in the room, we've got here a project that is to observe UV polarization. So it tends to make spectrum polarized. Okay. Okay. For a list of stars, and it should be a science demo because we don't have a measurement on specific on any stars actually, and in the UV, and it should be also a techno demo because of the huge challenge to observe UV and to have the stability that is requested for this kind of observation. So then it's a techno demo. It's at the moment in PDR, so preliminary design review, and we wait for CNES to approve the review. It should be a demonstrator for Pollux that should fly on ÖAW. Then completely different. So we are at on the opposite way, side of the spectrum. We have a project, a very long-term project of low frequency radio observatory around the moon. So it should be a swarm of 15 nanosatellites. And because it's low frequency, you have to be in space. Because it's low frequency, if you want to make interferometry, you have to have long baselines. Then a swarm of nanosatellites who provides baselines from 5 kilometers to 100 kilometers. It will pulsate spontaneously, so we can have multiple baselines at the same time. And we observe when we are on the far side of the moon, and we transmit the data when we are on the close side of the moon. And this should be, this is also supported by CNES, and we've got a PhD student finishing his study with that. So then, in this case, we've got a whole list of science cases that we are investigating at the very moment. So it should really become, if it's funded correctly, and if it's done, it should really become a new window on the universe, as we We just don't have the picture of the sky at low frequency.
What about LOFAR? Isn't that similar?
Yes, that's completely related. LOFAR is there were LOFAR and OLFAR. So LOFAR. Okay, OLFAR was an attempt to make LOFAR in space, and the rest of the story is noir. Okay, so that was taken over because there were not any volunteers anymore to push this long story. And then in France, we took that over, and we submitted to the French agency, and they said, okay, we should at least keep studying that further. Just to give you an idea, but should not spend too much time on that. So we are interested in signals that are here, roughly speaking. So auroras on planets, which are in terms of energy, 10 magnitudes below the noise that is generated by the Earth. So that's why we need to be hidden from the Earth. That's why we are beyond the. Okay, and now we've got also this project, which was another science case at the beginning. Now it's the idea is to fly by an asteroid in order to and make radio science during this flyby in order to have ranging and Doppler, then reconstruct the trajectory and derive the mass of the moonlet. Okay. So we know the mass of it because we've got a moonlet turning around, but how do you know the mass of this one, or how do you know the mass of an isolated object? Well, you can measure the deflection. And this project has inspired a lot of work, interplanetary navigation, proximity operations. It has also inspired some astrometry, which leads us to ABC for angular-based correlation. That is the subject of the topic. That is the topic of today. So I will go now more in the technical aspect of astrometry, why we need it, and so on. So at the beginning, we wanted to support Birdie as a part of the mission concept. We need to demonstrate that we could make an autonomous navigation. So an unscented Kalman filter was implemented, demonstrated in simulation and blah. We also coupled that with some radio science measurement, and we discovered that we could be accurate by a few meters in deep space, which was very good in terms of orbit determination, autonomous orbit determination. We assumed in this simulation an optical beacon. Optical beacons means so then we take a measurement of a foreground body before a background of star. At subarc-second accuracy, which was challenging, but we believe it was possible. And we should rely on CubeSat hardware, so CubeSat NewSpace. The problem is this assumption. This assumption was not trusted by any reviewer, so we had to demonstrate it first. And so that's how we started to develop this astrometry on board a CubeSat. And so the theoretical background is that if you make some smart quaternion algebra, very compact, and then you can estimate using so if your optical beacon is this one, and you've got 3 known stars in the field of view, well, with quaternion, you can make a very compact algebra that will use the fact that the interdistances, angular distances between the body and the stars are strongly intercorrelated. Okay, if I move this, all 3 will move as accordingly. And then there is only one location that can explain the measurement of multiple. That's what we put as a very compact way. And as a result of that, we can we can make an estimation of the exact position, so the measured position, x0 and y0, plus the estimated shift that should explain the measurement. Good, that's the fit. But in addition of this estimate, we can also extract the covariance of this estimate, which is strategic because this covariance can feed a Kalman filter without a priori assumptions. It's a real covariance. And if we are lucky, in the best case, we make some estimates and we see that we can get an improvement in the accuracy of the output that is improved by the number of stars, by the square root of number of stars. So this was expected, plus multiplied by a very small factor, which is the accuracy we had from a raw measurement, divided by the size of the cloud of stars. So the mean, the average interdistance of the star, which is the size of the cloud.
Got 20 minutes.
So, yeah, you what to yes, help or not by the current NewSpace. So large figure U is what we want. The larger, the better for the number of. Then, for instance, if I take a 10 point U, then we go for 5 degrees, and then we can expect 10 stars bigger than magnitude 6. 10 stars is better. Then it's an advantage. Photometry of the top, nobody knows. Nobody knows because every imager in the new space are dedicated to observe the bright side of the Earth. You see, we can distinguish an ocean from a boat. So, on the top, aberration, people to accept, no data, a lot about that. So, from young, you got a lot of cosmic that can increase the sensitivity of your plane or sensor just because you are hit by cosmic. Either they are or they become part of the space. So that's a real daylight.
Yes,
Typically the you want to make the standpoint of target. Then we have to do a lot. So, there is no what do you expect? You will see. So, but there are more and more on the major mathematics, the good news. That's really we don't have. And then it's going to be matter effects in the question of behind it. It is very concept to have sensors to decide. And how much? Then I will say it can be optimized for Earth, so maybe it's not possible. So the principle is on to look at the motion of beacons to triangulate mechanism of triangulation. And if I take a round observation, I can see that usually Jupiter and Saturn are still bright as we start behind. So I guess but there are red points and blue points. The blue points represent moons. Moons are on the same line of star. So you can use the moons to figure it compared to the star. Just want to each, and then you can use the moons. The remaining problem is going to run maybe your object is not there. So there are still many challenges to use. That's all what we what you don't, it goes easily do it. usually either you make star tracker meaning by question, or you make a picture in question. An image. We had where that was developed. And it was intended and then we got here an ADCS. Oh, I thought you know. So at the beginning, we realized that our ABC, but we could also use it to say how much unstable was the satellite. His first reaction, his first reaction was, Boris, we would really like to help you, but I'm afraid that our satellite is not stable enough for you to invest in stuff. What kind of problem do you have? Yeah, you have some concern. Don't talk about it. There had a stability concern with the ADCS. Then I suggested to use this ABC to assess, to characterize instability. And that's how it started. And then, if we want to use it for navigation, if we want to measure beacon, characterize if the ADCS is correct or not, reliable or not. So then, and if we need to, and we can also use this to characterize this ADCS. So finally, we could help each other. And we were known, we were told a pointing accuracy, a pointing APE means absolute pointing error from the data sheet, article, attitude knowledge error. Maybe it was so, so then here is the detail of the nanosatellite. After design to be not something. So we got here solar array on the sensor on the here so we can have a image here. So here you got the star tracker that goes to, and when you see that, how can you avoid stray line with this kind of battle? Yeah.
Didn't they apply any coding or a coding?
So this is done by, I'm sorry, Hyperion. But we lost the satellite, and everybody I knew this platform. So, an example of that bad. So then here on so you want to zoom, you take your time. And now you okay, then we've got also the start marker is pointing in the while the imager is pointing to the level. Okay. Otherwise, yeah, television of view okay, 30 axes from the refreshing at once. And quite well depth 12 bits. Okay, it's not so common. So we have this kind of orbit. So now obstacle is over. So then the concept of observation for ADC was to say we first start in the pictures. So we got our first images actually 3 weeks, quite full time on the stars. We got this contract to make this study, and there is a big one. Okay, so then in terms of operations, we had prefer operations with UpSat. So I told them for this month, point to this direction of the sky, then I can take into account their constraints. That was huge. So and this was the field of view of the star tracker. So we are looking at the Nadir, well, the minus 90 field of view, the mission rate. Oh. So this is the field of view that we request with the star in the middle. If we look at it this way, this is the field of the star tracker. So we make sure that the sun is not too close. This is the sun sensor field of view, and we combine all of this and we produce quaternion, we give them the quaternion, and they plan this quaternion in the operation. They take pictures. And I here we have we rapidly understood that actually the star tracker doesn't work if it is not in eclipse at all. So eclipse is maybe because of this lack of you expect the star tracker to work in eclipse and the eclipse that's 10 minutes. And it's 5 minutes. Make your we never use the data. Well, we did that one now designed to observe the data. And then we have to take into account many things, right? Picture, and then so the calibration start. This is the calibration start of the James Webb Space. So we are not expecting that. We're not expecting something else. But I believe this is not stuff. Well, this was just a poster. I found it. Right. So then we started to understand our wave, and we go a little more I agree, and there were a lot of like 90% of the country. And who these are cosmeters? After thousand, after giving quite high improvement, but it was not true. And then the star. So here is this is not the red and the red, the green is 5.2. That's randomly only one pixel over 4 million will be outside of the green. So it means that there is signal. There are the stars. Maybe some remaining. Okay, so once we could be once we were able to see the pixels, develop a technique, then more systematically, and actually to distinguish a good way. Then you can ask of the data. Here's my example. Without alignment. Then what does it tell you? It tells you the wobble over the 2.5 seconds exposure time. It tells you the wobble. It tells you the thickness of the line. It tells you the high frequency vibration. The next tells you the low frequency vibration. So the wobble. And if you stack them after realigning, that's the best PSF you can expect from a writer. Remember, PSF should be 1 arc. It means the real PSF is 50 arc seconds. So then, straight line of the bright star over the 50. So that's why you need to. But we could process that. We could process that, and we got we got the data set of usable stuff. But what and here's what's on input, and here's one. So 20 degrees into so that is not in 8 absolute point over 17 degrees. I need to do because we without a priori then we measure I will explain. I'll show you an animation that shows here the quaternion as estimated by onboard computer. And these quaternions are translated in the blue square. So there is a fine pointing and there is a fine ADCS and a core ADCS. So that's why there are that. Then we got the request is the white square. Green square. Okay. So then, so I'm figuring the time of. So what is this? That one go. Okay, I want to from there to the request. But so then now we really can the next involved. From there, we can assess the problem, and one of the hidden problems was probably because that well, probably the alignment. So from this measurement, we can make some assumptions about what we can very few data, but we could make an assumption that after was used according to the most of the total was divided by one of course, divided by the meeting. It was still on support page, but they didn't already. From there, we can also characterize the PW, so it means also like make a statistics about the number of people getting caught. Our expect so the idea is so we were not with operations when we were starting our algorithm itself. So we could run it, we could run it, but it didn't run on board the correct features. So we don't have and now what we are doing. So ADCS is not commissioned and thus should be kept. I want to trust the NewSpace. We need to have the power, the power and the authority to make serious commitment. So, well, and you are not by you buy a satellite, don't subcontract this. So now what the position and next line to access the sensitivity of that. We have we can consider then later Yes. So the idea at the end is to have, if we are requesting to make generalization, we provide one slide without any specification of it. I think to make this
I'm really interested in the comment there, that the low frequency rate is applied to the fan. Because, I mean, basically, the whole new people told us that the relation astrometry is thinking about, because it's the whole space, right? But the problem is that we are saying, how good do we actually communicate between satellites and flights to make the right language?
So for the radio switches, well, there are multiple time scales. So there are the short time scale for the exposure time. So then there are by one
How do you make sure that the baseline is made or
no, it's moving slow.
Oh,
Okay, because a swarm, well, and the whole swarm is jettisoned roughly at the same time. They have a very small delta V from one to another. Then, as a result, the optical parameters vary from a very small. Just with that, you got a pulsating swarm. Just imagine you got one in a very perfectly circular orbit. You got a second one with just a little orbital parameter difference. It will be a small ellipse. As seen from the first one, it will be a quasi-satellite orbit. The circular one will be orbited by the ellipse one as an artificial satellite. We do that with all the satellites. So the periodicity of this is one of the. So it's slow, but indeed it's changing because it's changing. Yes, that's now our motion. Yes. So the baseline, all the baselines